Hello everyone, this video covers section 4.5. The title is Romper Integration. Before we get into the section, recall from section, I believe it was 4.2, we did Richardson extrapolation for derivatives. So now we're doing integration. So what we're going to do in this section, technically we're going to apply Richardson extrapolation to integrals. We're going to focus specifically on the composite trapezoid method, and the idea of the Richardson extrapolation, which is going to be called Romper integration now, is the following: that we're going to get a high precision. So we're going to get high precision, and remember here precision is related to the value of h. So high precision with little computational costs. And computational cost means the method we're going to use. The trapezoid is straightforward. These values are given or are easy to compute, and you just have to add it up. Now, by definition, remember the composite trapezoid rule has the following error function or truncation error, which this is big O of h squared. So we talked about that a few times. Now, if you remember from Richardson extrapolation, there we use this notation m equals to n1 of h, and then k h squared, and so forth. So in this section, this is the analogous of that, and the idea is that we want to increase from h squared to h to the 4 or h to the 6 and so forth. But in our particular case, n1 is going to be just the trapezoid or the composite trapezoid rule. Okay? So it's very, very similar to section 4.2, except that here we're integrating instead of differentiating. Now, for this to be possible, this assumes that f has an infinite number of derivatives that are continuous, which obviously is not the case for all functions. And remember, this by definition is big O of h squared. We will be using the following notation: R11, R21, R31. From section 4.2, this is equivalent to the n1 of h that we used before. Okay. So the question is, what is R11, R21, and so forth? R11 represents the original trapezoid method. By original, I mean this. Remember, let's say you have a function that looks like this, and you go from A to B. You create just one trapezoid at this point and at this point. And this was the original trapezoid, not composite, the original trapezoid method, and this is what we call R11. Now, if you divide the interval in half, so this is still A, it's still B, and you still have the same function, or kind of the same function, but now we divide the interval into two pieces. So then this and this will be what we call R21. So now we're using this formula, and if you cut the interval again in half each of them, so if this is A, this is B, you still have this function, and now you cut this into two pieces each, you will get a more accurate approximation, and this is what we call R31. Now all of this, R11, R21, and R31, all of this will be O of H squared. That will be the precision. So just like in 4.2, the goal of the extrapolation is to go from H squared to H to the 4 or H to the 6 and so forth. Now this formula is going to give you a recursive way to come out with more precise answers. Here k should be equals to j plus 1, j plus 2, and so forth. So for example, if you want to get O of h to the 4, then you need to find rk2. So j would be 2. So therefore, you could get rk1 using the formula plus 1 over 3, and you should check that this is the values that we get from here by substituting j equals to 2. And then this will be rk1, which we have these values from before, minus rk minus 1 and 1, where these values will be the values that have big O of h squared. All right, again, this will be true for k equals to 2, 3, and so forth. For example, R22, which is equals to R21, remember this is already known, plus 1/3 R21 minus R11. This is known, this is known. This computation will be O of h to the 4. Now, if we want big O of h to the 6, then you will have to find R k of 3. So this will be rk2 plus 1 over 15 rk2 minus rk minus 1, 2, and then you just have to follow it's pretty much just this formula again. And now the values for k here, it will be at 3, 4, and so forth. So therefore R33 will be OH6, big O of H6. Okay, so let's do an example and see how this works. All right, so let's say we want to integrate 4 over 1 plus x squared from 0 to 1. So remember, R11 is the original trapezoid, which is just going to be equals to h over 2 times f of a plus f of b, where for this one, for this particular case, h is just b minus a. So therefore, in this particular case, this will just be 1 over 2. That means h is equals to 1. And then this will be f of a, which will be 4 over 1 plus 0 squared plus 4 over 1 plus 1 squared. And this is equals to 3. So you should check that. And remember that this one is big of h squared. All right, so then R21 will be 1 over 4. And this will be now 4 over 1 plus 0 square plus 2 times 4 over 1 plus 0.5 square, and then plus 4 over 1 plus 1 square. and this is 3.1, and this one is also O of h squared. Now just keep in mind that the h for this one is slightly different. Remember, the h for this part is equals to 1/2, so that's why 1/2 or 1/2 gives you 1/4. Now if we find out our 3/1, so then this will be 1/8. If you divide h over 2 again, it will give you 1/8. It will be 4 divided by 1 plus 0 squared, and this will be 2, then 1 plus 0.25 squared, 4/1 plus 0.5 squared, and so forth. So this is very easy to compute. It just takes time to do by hand. And then finally 1 plus 1 squared, and this is equals to 3.1311767. Now you should verify this yourselves. So you continue in this way, which means now you divide h by 2 again, so that will give you 1/16. The value you get is 3.1389949, and then R51, and please just verify this, is 3.14094161. And remember that this one is also big of h squared. This is also big of h squared. So now let's find an approximation of h to the 4, or big O of h to the 4. So for that, we need to find now R22. Remember that this is equals to R21 plus 1/3. So you just have to follow the formulas we just find out in the previous page. R21 minus R11. And then this will give you 3.1 plus 1/3. This is 3.1 minus 3. And once you simplify, this is 3.1333. It keeps going. Okay. So remember, this one now has a precision of big O h to the 4. The same thing is going to be true for R32. This will be R31 plus 1/3, R31 minus R21, which we have all of these values, and once you plug it in, this equals to 3.14156862. And one more time, this is precision big O of h to the 4. Notice how this is approaching to pi, and that should not be surprising because that's the exact solution, like I will show you in 1 second. So now if you want to find precision of big O h to the 6, then we will need to find R33. So R33 will be R32 plus 1/15, R32, which we already have now, minus R22, which we also have. And once you plug in the values, this is equals to 3.14211,774. And remember, this is precision of big O of h to the 6. Now if you keep going and you find R55, this is actually equals to 3.1415 9274, which is very close to the value for pi. Now by following that formula, you technically create the following table. Let's say the values for k are 1, 2, 3, all the way to n, and then we start with big O of h squared k. The reason why you have the k here is because the h at every step is not the same, and by that I mean this. Even though all of these are O of h squared, notice that the value for h in this case is not the same thing as this case, so you just have to be aware of that. So that's why we need the subscript k there. So then this will be R1, 1, R2, 1, R3, 1, and so forth until Rn 1. This is the composite Simpson that we use. Then if we move to the next position, you need the k again. So this will be now R22, R23, sorry, R32, and so forth all the way to R and 2. And if you want the next position, then this will be R33, R and 3, and so forth. So this keeps going this way. It keeps going this way. So therefore the big O h of 2 to the n k will be the best and last precision you can get will be Rn. Now before we go to the last formula we have here, remember that the exact solution in this case, the integral from 0 to 1 of 4 over 1 plus x squared dx is equals to tangent inverse times 4 of x from 0 to 1, which is 4 times pi over 4 minus 0, which is just pi. And you can see this is very close to pi. Now you can also use this formula if you want to find a recursive way of figuring it out, the k1, where k is equals to 2, 3, 4 all the way to n, which is technically these values right here. Okay, so you don't want to compute it separately, you can just use this formula. And notice how this is keeping track of the different values of h. In fact, here h to the k is equals to b minus a divided by 2 to the k minus 1, which means at every step you are dividing the interval in half. Okay, and that's it. Now the hard part here, which I believe is one of the homework questions, is how do we get these formulas, because here they just were given to you. So I do believe there is a question where it does explore how to find these formulas, which is very similar to using the methods we did in section 4.2. All right, so that's it for section 4.5.